Good morning, children. Today we are going to discuss the 7th unit of our syllabus, dual nature of matter and radiation. It is the third chapter of part second of NCERT textbook. It comes in our second term. So unit number is dual 7th. It is dual nature of matter and radiation, in which we have to establish that matter and radiation both are dual in character. That means matter under most circumstances behaves like particle, but under certain circumstances it behaves like a wave. Similarly, radiation under most circumstances behaves like a wave, but under certain circumstances it behaves like a stream of particles. That is what we call dual nature of matter and radiation. And we know there is a relation which connects the wave nature and particle nature of both of these radiation and matter. That relation is called de Broglie's equation, which says lambda is equal to h by p. We have to discuss that. So first we have to discuss here photoelectric effect. Now, what is photoelectric effect? Photoelectric effect is an effect which by definition is interaction of matter and radiation, in which light is incident on some metal surface. If light is energetic enough, it extracts electrons out of the metal surface. Now, the electrons which are ejected out of the metal surface, because of this light exposure to that metal surface, those electrons we call photoelectrons, and this effect is called photoelectric effect. Now, how we experimentally discuss this effect? We will discuss first that. The experimental setup to understand this effect is like this. You can draw this figure. There are two electrodes, one named as emitter, E stands for emitter. Second electrode is called collector, C stands for collector. Then we externally apply voltage across the electrodes. So I will draw first it. It is radiation. In this tube inside there is vacuum, and this is quartz window. The experimental setup is like this now. We have two electrodes. We want to understand, study the photoelectric effect. For that we take two electrodes, one called emitter. Emitter is called emitter because ultimately photoelectric effect will take place at the emitter. Emitter will emit electrons, which we call photoelectrons. Then we have one more electrode called collector, which we have labeled by C. C stands for here collector. Collector is called collector because ultimately it is going to collect the electrons emitted by the emitter. Now, externally, this V external establishes potential difference across emitter and the collector. Now, here is sliding contact. This sliding contact ensures that we can have variable external voltages across emitter and collector. If we move the sliding contact, accordingly voltage across emitter and collector will be changed. This is here a voltmeter. Voltmeter is connected across emitter and collector, which will give us measurement of the voltage across the emitter and collector. Then we have one more current meter, ammeter here. This ammeter will measure the current. Which current? When electrons from the emitter will reach collector, current in the external circuit will flow. That current, called photoelectric current, will be measured by this ammeter. Now this, we know conventional current, direction of conventional current is opposite to direction of flow of electrons. That means if electrons are flowing in this loop this way, conventional current will be going in opposite sense like this. This current will be measured by the ammeter which is connected in the loop. This current we call photoelectric current. So I here is our photoelectric current. Now situation is like this. We have two electrodes, emitter and collector. Light of suitable frequency is incident on a given metal surface of the emitter. Then if its energy is sufficient to extract electrons of the emitter, electrons of the emitter will be ejected. They will be collected by the collector. In external circuit, current will flow. That current we will measure by the assistance of this ammeter. This voltmeter will read the applied voltage. Then what we do, first we need to understand here, the voltage across the emitter and collector is algebraic sum of two voltages. If V stands for the voltage across emitter and collector, it is algebraic sum of two voltages. One is the voltage which we externally apply by this battery, V external, plus there is one more voltage which I am writing as V subscript CPD. This is called contact potential difference. Now what is contact potential difference? If there are two materials which are dissimilar in nature, there is always some potential difference between dissimilar materials. We call that potential difference as contact potential difference. Now in studying this photoelectric effect, in most of the circumstances, emitter and collector electrodes are made up of dissimilar materials. Therefore, there is already a contact potential difference between emitter and collector. And we are externally applying this voltage using this battery. Therefore, the overall voltage across emitter and collector will be algebraic sum of these two, externally applied voltage and the contact potential difference. If situation is like this, that emitter and collector are made up of same material, then this contact potential difference is 0, and here V will be simply equal to V external. And one more thing, what we do in this experiment, we change this voltage and see the effect of that change in voltage on the photoelectric current. Sometimes we change the frequency of the incident light, keeping metal surface fixed, and see what is the effect of that change in the frequency on the photoelectric current. And we may change another parameter, that's called intensity of light, keeping frequency of the light fixed, and see what is the effect of that change in intensity of the light on the photoelectric current. When we do it, we have found certain results in this experiment. Those results are like this. One result is indicated by this graph. What is this graph? This graph is photoelectric current I versus voltage, potential difference. Potential difference across emitter and collector, which includes contact as well as externally applied voltage by the battery. I will draw these curves, then we will explain this. Let this be curve A, Let this be curve B. Now, what is represented by negative zone of this graph? And what is represented by the positive zone of this graph? In positive zone of the voltage, we are connecting emitter to negative terminal and collector to positive terminal. That means when the potential difference V is positive, at that time the applied voltage V will help the collection of electrons by the collector. Because when emitter will be negatively charged, when electron is extracted by the light, that negative charge of the emitter will push the electrons and the positive charge of the collector will pull them. Therefore, the voltage applied across emitter and collector will help the collection of the electrons by the collector and help the flow of current, photoelectric current. In this negative zone of the graph, emitter is connected to positive terminal of the battery and collector is connected to negative terminal. At that time, what will happen? The applied voltage will oppose the collection of electrons, because when emitter is connected to positive terminal, electron will not be easily, electron has to overcome the attractive force of that positive in order to reach collector. And when collector is negatively charged, it will not accept on its own the electron emitted by the emitter. Therefore, in this zone of the plot, when emitter is connected to positive terminal, collector to negative terminal, electron has to overcome the attraction of the emitter and the repulsion of the collector in order to reach to the collector. That means in this zone of the voltage, applied voltage is opposing the motion of electrons from emitter to collector. In this zone of the graph, applied voltage is helping the collection of electrons by the collector emitted by the emitter. Now, what we do in curve A and curve B? In curve A, we have selected some metal surface of the emitter and selected some frequency of the light at which photoelectric effect takes place. We have to take that particular frequency, only then we can understand photoelectric effect. So, in curve A, we have selected some metal surface of the emitter, then we have selected some frequency of light at which photoelectric effect takes place, we have selected certain intensity of the light. So, when we do it, we see first on increasing the voltage, this current increases and then it gets saturated. The saturated value of this photoelectric current is called saturation photoelectric current. And in curve B, what is different as compared to curve A? In curve B, we have same metal surface of emitter as that of A. We have same frequency of the light, but we are doubling the intensity of the light. So there is only one difference in curve B and curve A. We have doubled the intensity of the light in curve B compared to curve A. And what we see experimentally, when we are doubling the intensity of the light, keeping frequency of them and the metal surface constant, the saturation photoelectric current doubles. So this distance is approximately twice of this. In graph approximately, but in reality, in experiment, it is 100% twice. So we are seeing when we double the intensity of the light, saturation photoelectric current doubles. The one experimental fact about the photoelectric effect is, if we keep the intensity, if we keep the frequency of the light constant, metal surface fixed, saturation photoelectric current is directly proportional to intensity of the light. Similarly, if we make the intensity thrice, saturation photoelectric current will become thrice. This is one experimental fact. Second thing, what is this negative voltage called? We represent this value of voltage at which photoelectric current is reduced to 0. We denote it by V0. And this V0 is called stopping potential. Now, what is this stopping potential and how we define it? We can define this stopping potential as the minimum negative voltage applied across emitter and collector at which the photoelectric current reduces to 0 or photoelectric current drops to 0. That means at all negative values of voltage, greater than stopping potential and equal to stopping potential, photoelectric current will be 0. Now this stopping potential we see from experiment. When we are changing the intensity, in curve B intensity is twice of curve A, saturation photoelectric current has doubled, but there is no effect on the stopping potential. That means we can say the stopping potential is independent of the intensity of light. There is one more graph in this experiment in which we plot the stopping potential versus frequency of the light. That means we select some light, fix its intensity, then we change frequency. That means we can go from visible to ultraviolet to infrared. That means we are changing the frequency of the light. We see experimentally stopping potential is directly proportional to frequency of the light, keeping intensity fixed. And from graph we see there is a minimum value of frequency when we plot stopping potential. On this side it is stopping potential, on this side it is, nu is representing here frequency of the light. So this value of frequency, nu naught, we call threshold frequency. We call this threshold frequency. Threshold frequency is the characteristic of the metal surface. Now what is the interpretation of this plot? Stopping potential is directly proportional to frequency of the light, and there is a minimum value of frequency called threshold frequency represented by nu naught, which is characteristic of the metal surface, at which stopping potential is 0. So at nu naught stopping potential is 0. Now we want to interpret these graphs in detail. First we look at this graph. From this graph we observe that when there is no voltage, that means when there is no opposition or no support by the external voltage, still there is some photoelectric current. That means even when there is no voltage across the emitter and collector, some of the electrons reach collector which contribute to the current. So there is current flowing in the circuit even when there is no voltage. And when we increase the resistance of the voltage, saturation current increases and reaches the saturation value. And on this side of the plot we see when voltage is made negative, that means these connections are reversed. What happens there? Current reduces, ultimately at stopping potential becomes 0. So from graph we can say the current contributed by the electrons which contribute current in this zone must be moving faster compared to the electrons which are contributing current here. Why so? Because in this zone electrons have to overcome the opposition to reach the collector, and they can overcome that only when they are moving fast. Their kinetic energy should be large. Therefore, in this graph, kinetic energy of the electron is large, and as we move towards stopping potential, that means to the left of this plot on negative side of the potential difference, the kinetic energy of the electrons contributing the current increases. At stopping potential, the most energetic electrons in the lot, by that I mean when light strikes the emitter, electrons which leave the emitter surface do not have same kinetic energy. Some are moving fast, some are moving slow. At stopping potential, even the fastest electrons cannot overcome the opposition. Opposition is huge. Therefore, the fastest ones stop at stopping potential. There is no current. Now we know from conservation of mechanical energy, for example, if I throw some body in upward direction in this gravitational field like this, when it goes up, what happens to its kinetic energy? its kinetic energy reduces, but its potential energy increases. When it reaches the top, its kinetic energy becomes 0 because it momentarily comes to rest. But at that moment, when it comes to rest at the top, its potential energy will be equal to the kinetic energy at the point of throwing. That means when I throw it, whatever the value of initial kinetic energy there, it appears as the potential energy at the topmost point of its trajectory. That means at the topmost point when it momentarily comes to rest. It is this kinetic energy which gets reduced as it goes up, moves up, that becomes potential energy at the top. Same idea is here. At stopping potential, it is the stopping potential which breaks these electrons. And we know delta U is equal to Q delta V. That means if some charge Q moves between 2 points having potential difference delta V, then the change in its potential energy will be Q delta V. Using this idea, I can therefore write K max. What is K max? K max here is the kinetic energy of the fastest moving electrons in the lot which are emitted by the emitter. The fastest ones, their kinetic energy will be maximum in the lot. So K max must be equal to EV naught. What is E? E is the charge on the electron. Because at this stopping potential, V naught becomes our potential difference. Instead of Q, we have charge on the electron. And it is the potential energy which becomes equal to, which is the kinetic energy of the fast moving electrons, which ultimately becomes potential energy when they are braked, when they stop. Therefore, I have one more result. K max is equal to EV naught. K max is the kinetic energy of the fastest moving electrons, E is the charge on the electron, V naught is the stopping potential. Now we can draw one more conclusion. Experiment says stopping potential is directly proportional to frequency of the light. K max itself is proportional to stopping potential. Therefore, K max will be also directly proportional to the frequency of the light. That means if we keep frequency constant, K max will not change because stopping potential will not change. If we double frequency of the light, it will double the stopping potential and hence it will double the K max, kinetic energy of the emitted electrons. And if we change the intensity, keeping frequency constant, changing of intensity will not change stopping potential. It will change the saturation photoelectric current. It will not change stopping potential, hence it will not change K max. Hence it will not change K max. So experimental findings can be summarized like this. In photoelectric effect, experimentally, the saturation photoelectric current is directly proportional to intensity of the light. Stopping potential and hence K max is independent of the intensity. Stopping potential and hence K max is directly proportional to frequency of the light. And there is a value of threshold frequency represented by nu naught at which stopping potential is 0. If stopping potential is 0, therefore at nu naught, K max will be also 0. At nu naught, V naught is 0, stopping potential is 0 from the graph, K max is EV naught, therefore K max will be 0. That means at a frequency equal to threshold frequency or less than that, fastest electrons are even at rest. Slow ones will be always at rest there in this situation. So in other words, at nu equal to nu naught or less than nu naught, there will be no photoelectric effect. No electron from emitter will reach to the collector. Now question is, can we explain these experimental findings using the wave nature of light? We will justify it is not possible to account for the experimental findings in this effect if we consider light as an electromagnetic wave. We will discuss that. Explanation of photoelectric effect using wave theory of light. Explanation of photoelectric effect using wave theory of light. So we will try to explain photoelectric effect, that means the experimental findings of a photoelectric effect using the wave theory of light, that means treating light as an electromagnetic wave. When we try to do this, there are three problems which arise. One problem is called the intensity problem. What is that? The intensity problem. If the intensity means energy transported by wave per unit area per unit time, and for electromagnetic wave, intensity is written as 1 by 2 mu naught C E m square. This is the expression for intensity of electromagnetic wave. I here is intensity. Mu naught is permeability constant, permeability of free space. C is speed of light in vacuum. What is EM? EM is the maximum value of the electric field, amplitude of the electric field in the wave. We know in electromagnetic wave, electric field is oscillating. This EM represents the maximum value of the EM present in the wave, amplitude of electric field. That means if we treat light as a wave, if we increase the intensity of the light, wave theory says that will increase the maximum value of the electric field present in the wave. And accordingly, all lower values will increase. If you increase the peak, these values are going to increase. You are changing the overall waveform, amplitude wise. The wave theory says if you increase the intensity, you are increasing the electric field, and if you are increasing the electric field, we know electric field exerts force on charge, and that expression is F is equal QE. If charge Q is placed in electric field E, then the force experienced by the charge F is equal to QE. Therefore, force on the electron will be minus EE. Because charge of electron is minus C. Force on it will be oppositely directed to electric field. Now important here is, if you are increasing the amplitude, magnitude of force will increase. If you are increasing the intensity, that will increase the maximum value of the electric field, that will increase the maximum value of the force, which will be experienced by electrons due to electric field present in the wave. Now when force will increase, you are pushing something with more force, so it is obvious that its kinetic energy should increase. That means wave theory says increase in intensity of the light must lead to increase in kinetic energy of the emitted electrons, and we know K max is equal to EV naught. Therefore, increase in intensity must lead to increase in stopping potential. So there is 100% contradiction. Experiment says there is no effect of changing intensity on stopping potential and kinetic energy. That means kinetic energy and the stopping potential are independent of the intensity of light. Wave theory says kinetic energy and stopping potential must change by changing the intensity of light. So it is not a minor deviation, it is 100% contradiction. That means we cannot account for this experimental fact using wave theory. Now, there is one more problem. Second problem which arises when we try to explain photoelectric effect using wave theory of light, that is called a frequency problem. What is that? Experiment says if you have some metal surface, if it is some metal surface, for this metal surface there is a characteristic value of frequency nu naught called threshold frequency. It is threshold frequency. If the frequency of light which you are using to extract electrons of the metal surface, if its frequency is less than or equal to threshold frequency, less than or equal threshold frequency of the metal surface, whatever its intensity, no photoelectric effect will take place, because at nu equal to nu naught or less than nu naught, stopping potential is 0, Kmax is 0. No photoelectric effect takes place at that particular frequency. Experiment says for every metal surface, whatever the value of intensity of light, if the frequency of the incident light is less than or equal to threshold frequency of the metal surface, no photoelectric effect will take place. But wave theory says, since we have said it, intensity of the electromagnetic wave is 1/2 mu naught c Em square. Therefore, according to wave theory, we can say whatever the value of frequency, or we can say this way also, for all metal surfaces, according to wave theory of light, photoelectric effect must occur for all frequencies of light, provided intensity of the light is large enough so that electric field present in the wave is large enough so that force equal to EE is large enough to eject electrons out of the metal surface. So there is no question of threshold frequency in wave theory. Wave theory says for all metal surfaces, photoelectric effect must occur for all frequencies of light. Only intensity of the light should be large enough so that electric field present in the wave is large enough so that force experienced by the electron is large enough to extract it out of the metal surface and make it move to reach to the collector. So there is one more deviation. Experiment says one thing, wave theory says different thing. There is third problem. Third problem is called time delay problem. What is that? In wave theory we say energy is uniformly distributed over the wave front. When wave strikes the metal surface, some portion of the wave front will strike the metal surface. Accordingly, the electron available in that zone has to soak the energy from the wave front in order to escape the metal surface. Now, when we write intensity as power per unit area, P represents power, A is area. Power itself is energy transported per unit time. Therefore, I can write I equal delta E by delta T into A. Delta E by delta T is representing power. I solve for delta T. Delta T will be delta E by IA. Delta T will be delta E by IA. Now, for a given amount of energy required for the electron to escape the metal surface, according to wave theory, if intensity is small enough, it is possible to increase the time interval required for the electron to soak the required energy from the wavefront in order to escape. The effective area over which electron can extract energy from the wavefront is small. Electron will be available at most in a region having diameter equal to that of atom. Within that zone, electron will be available. That atomic diameter is small, therefore effective area over which electron can extract energy from the metal surface is small. Therefore, the required energy can take long time if intensity of the light is made small. That means, according to wave theory, it is possible if photoelectric effect takes place at some particular frequency of light, it is possible if we make light feeble enough, if we reduce its intensity, it is possible to increase the time interval between what? Between impinging of the light on the metal surface and the ejection of electrons from the metal surface. If it is possible to make it 1 week, it is possible to make it 1 year by reducing the intensity accordingly. But experimentally we say, whatever the value of intensity, if frequency is suitable for photoelectric emission, whatever the intensity, whatever small its value may be, photoelectric effect is always instantaneous. No time delay between impinging of the light on the metal surface and the ejection of electron has ever been observed. So we say photoelectric effect is always instantaneous. There is no time interval between striking of light on the metal surface and the ejection of the electrons from the metal surface. So there is 100% contradiction between wave theory and the experimental findings of photoelectric effect. That's why we say, if we treat light as an electromagnetic wave, it is impossible to explain photoelectric effect. Then what we do? Therefore, we have Einstein's theory. Explanation of photoelectric effect using particle nature of light. Einstein in 1905 explained photoelectric effect, but not by using wave theory, because we justified wave theory cannot explain it. So he changed the idea. He said, under most circumstances, light is behaving like a wave, but under certain circumstances like this, there is one more, like Compton effect, where light behaves as a stream of particles. So Einstein said we can explain this photoelectric effect only if we treat light not as an electromagnetic wave but as a stream of particles, stream of energy packets. Each energy packet is called photon. And Einstein said energy of a photon is proportional to the frequency of the wave to which the photon will belong. If E is the energy of a photon, nu is the frequency of the wave, h here is Planck's constant, having value 6.6 into 10 raised to minus 34 joule second. Now Einstein explained in 1905 using this idea all the experimental findings of photoelectric effect. See how. So Einstein said, you have to treat light as a stream of particles. These particles are energy packets. They are not routine particles like some stone. They are energy packets. Each packet has energy proportional to frequency. That means if you take the photon of ultraviolet light, frequency of ultraviolet light is, wavelength of ultraviolet light is smaller than visible, frequency is larger than visible. Therefore, the photon of ultraviolet light will have more energy than the visible light. So, if you increase the frequency of the light, photon becomes more energetic, it is proportional. Now, how Einstein explained? First idea of Einstein was single photon interacts with single electron. So, there is no question of time delay. Photon will strike the electron. If energy of the photon is sufficient to extract electron out of the metal surface, photoelectric effect will take place. If not, there will be no effect. But there is no question of energy uniformly distributed over wavefront, as wave theory says. So he said this effect has to be instantaneous because single electron interacts with single photon. So there is no question of energy being spread over wavefront. Therefore, it is not possible that there can be time delay. It will occur instantaneously. So there is no question of time delay. Now, how he solved the problem of frequency and the intensity problem which arise when we try to explain it using wave theory. So he said, if h nu is the energy of the photon, when it strikes the metal surface, it will be used in two things. One is phi, second is k max. What is this phi? When photon strikes the metal surface, the electron present in the metal surface is bound. It is bound by the attractive forces present in the metal surface. First, you have to make that electron free. So, when photon strikes the metal surface, first this photon has to overcome the attractive forces by which electron is bound to that metal surface. It has to do work. For that, it has to spend some energy. That is represented by phi. This phi we call work function of the metal surface. It is work function. Therefore, part of the energy of the photon will be used by the electron in becoming free. That is represented by work function. The remaining part, that means h nu minus phi, will appear as kinetic energy of the electron, which will help the electron to reach to the collector. This equation is called Einstein's photoelectric equation. So here we need to first define work function. When we talk of some metal surface, all the electrons present in the metal surface are not bound to the metal surface to the same extent. Some are easy to extract, some are difficult to extract because of the difference in their binding. Work function of a metal surface by definition is energy required to extract the least bound electron in the metal surface. Therefore, least bound electron will have the maximum kinetic energy among the lot which is ejected out of the metal surface. And one more thing here is the idea of collisions. When the electrons come out of the metal surface, they may experience the collisions with the other atoms and electrons available inside the metal surface, and they may lose some of the kinetic energy. The electron which experiences more collisions will have less kinetic energy compared to the electron which experiences less collisions. That's why when these electrons leave the metal surface, one reason, different amount of collisions experienced by the electrons, and one more thing, all electrons are not bound to the same extent. Therefore, all cannot have same kinetic energy when they leave out of the metal surface. So, when in this expression we write work function, we talk of the maximum. That means this maximum kinetic energy is of that electron which is least bound and which experiences least number of collisions. Other electrons will have this amount of energy less, their kinetic energy will be less than maximum. Now Einstein said part of the energy of the photon is used up in making the electron free, the remaining part appears as kinetic energy. Now he has to explain the intensity problem and frequency problem. He said when we are increasing the intensity of light, what we are doing, we are actually increasing the number of photons striking the metal surface per unit area per unit time. So according to Einstein, increase in frequency means increasing the number of photons striking per unit area per unit time. So if you are increasing the intensity, keeping frequency fixed, you are not changing the energy content of the photon. If you are not changing energy content of the photon, for a given metal surface work function will be fixed, therefore you are not changing the Kmax. That means according to Einstein, if frequency is kept constant, doubling the intensity will not change, the photoelectric process will not change the energy content of the photon, therefore will not change the Kmax, therefore will not change the stopping potential, because Kmax is proportional to stopping potential. But it will certainly double the number of electrons ejected out of the metal surface, because single photon interacts with single electron. If you are doubling the number of photons striking per unit area per unit time, you are doubling the number of electrons, photoelectrons ejected out of the metal surface. That's why saturation photoelectric current doubles. So it is clear that increase in intensity will increase the saturation photoelectric current, or more appropriately, intensity and the saturation photoelectric current are directly proportional, but Kmax and stopping potential are independent of intensity. But if you change the frequency, you are changing the energy content of the photon, that will change the Kmax and hence stopping potential. Therefore, stopping potential is directly proportional to frequency, because increase in frequency will directly affect the energy content of the photon, accordingly will directly affect the Kmax, will directly affect the stopping potential. Now what is second problem? Second problem was the idea of threshold frequency. So Einstein said when nu is equal to nu naught, threshold frequency Kmax is 0. At that time this equation predicts h nu naught is equal to phi. So Einstein said if your frequency is equal to threshold frequency, which is characteristic of the metal surface, then the energy available in the photon is just equal to work function of the metal surface. That means the photon has energy sufficient to make the electron free, but there is no extra energy available in the photon which can appear as kinetic energy, by which electron can move and reach to the collector. Therefore there can be no photoelectric effect. It only makes electron free, it cannot make it move, because there is no extra energy. And if nu is less than nu naught, the energy in the photon will be less than work function. It cannot even make it free. So there is no question of movement of the electron from emitter to collector. So it was justified by Einstein that if frequency is less than or equal to threshold frequency of the metal surface, whatever intensity, that means whatever the number of the photons striking the metal surface per unit area per unit time, there is no photoelectric effect. Now there was the confirmation of the theory of Einstein. Now how this was confirmed? Experimentally, stopping potential was directly proportional with frequency, and this value of frequency was threshold frequency. Einstein said, my photoelectric equation also predicts the linear relationship between stopping potential and frequency. How? Put Kmax is equal to EV naught because K max is equal to EV naught, we know that. Solve for V naught. So we will get V naught is equal H nu minus phi. This phi we will take to the left hand side, it will become minus. Then E you have to divide by E by E. Take this this phi to left hand side, it will be H nu minus phi. Then E you have to divide, it will become nu naught is equal H by E nu minus phi by E. This is constant, and you can see nu naught versus V naught versus nu. Stopping potential versus frequency. This is the equation of a straight line with slope H by E and negative intercept minus phi by E. So he said my equation is predicting the linear relationship between stopping potential and the frequency as is obtained from experiment. And he said, according to my equation, the slope of this line, slope of the experimental curve, must be H by E. That means the value of H you can obtain by multiplying slope with E, charge of electron. Then the slope of experimental curve was taken, it was multiplied by E, charge on the electron, and when you do it, the value of H turned out to be 6.6 into 10 raised by minus 34 joules second, which was already established value of H. Since it matched that value, it confirmed the Einstein's theory. So right now, it is an established fact that light has a dual character. Under most circumstances, it behaves like a wave, but under certain circumstances, one of them is photoelectric effect. It behaves like a stream of particles having energy proportional to frequency, which we call photons. Now, light has a dual nature. Now, there is one more topic, wave nature of matter. Now it was established in 1905 that radiation has dual nature. Photoelectric effect justified its particle nature. Now dual nature of light was established. Now question was, do matter, which we under most circumstances treat as particle, is it possible for this matter to have wave character? The question was that. Now in 1924, Louis de Broglie he only suggested on the basis of symmetry. He said matter and energy are interconvertible. We know from pair production and pair annihilation that energy is convertible 100% to matter and matter is convertible to energy. And we know that we treat energy and matter both forms of energy. Energy mass equivalence relation we know is equal to mc square. That means m mass is equivalent to mc square energy and E energy is equivalent to E by c square mass. So they are equivalent things. Therefore, in 1924, Louis de Broglie said that matter must have wave character. And the wave character and particle character must be connected by the same relation as is for radiation, energy. What was that relation? We know if there is some surface and radiation is put on it, if U amount of energy, or I write E amount of energy is absorbed by this surface from this radiation, then the momentum delivered to the surface, if it is 100% absorbed, is E by C. P is the momentum delivered to the surface by the radiation, E is the energy absorbed by the radiation by the surface, C is the speed of light in vacuum. Therefore, if I write instead of E, h nu, treating light as a stream of photons, then I write P is equal to h nu by C, and we know C is equal to nu lambda. This is the relation. Therefore, I can write C by nu as lambda. I can write P is equal to h divided by C by nu. I can write it. C by nu will become lambda. Therefore, P will become h by lambda. Therefore, lambda will be written as h by P. So, this relation was already available at the time of de Broglie, 1924. That there is a relation lambda is equal to h by P, which connects the wave nature and particle nature of light, because it connects the wavelength and the momentum of the photon. Momentum is the particle characteristic. It is a property of particles. Wavelength is the wave characteristic. H is Planck's constant. So this equation is connecting wave nature and particle nature of light. Louis de Broglie said same equation must connect the particle nature and wave nature of matter also, because on the basis of symmetry, he said, if matter and energy are both can be treated on equivalent grounds from E is equal to mc square, both are interconvertible. Therefore, what is true for light, radiation, must be true for matter also. Therefore, he extended this relation, only he suggested, it was not experimentally established at that time, it was later established. He suggested matter must have dual character also, and same equation will govern the dual character of matter also. So his idea was, if there is some free particle which is not bound, free particle which is moving with linear momentum p, then associated with it there is a sinusoidal wave having wavelength given by lambda is equal to h by p. If there is a free particle moving with linear momentum p, then corresponding to it there is a sinusoidal wave having wavelength lambda equal to h by p. When we calculate the wavelength of, this is called now de Broglie's equation, when we calculate the wavelength of some materialistic particle, from this equation we say we have calculated its de Broglie wavelength. Then question was to test this equation, whether it is right or wrong. Before that, question was to experimentally check whether matter which under most circumstances behaves like a particle, is there some circumstance in which it behaves like a wave. Second question was, is the wave nature of matter same as predicted by de Broglie? It was experimentally confirmed by Davison and Germer, which is our next topic. We have to discuss Davison and Germer experiment. What is that? Davison and Germer experiment comprises of measuring the wavelength of electron beam. Davison and Germer measured the wavelength of electron beam. If we measure wavelength of something, it is sufficient to prove that is a wave. We know in 1801, same thing was done by Thomas Young in Young's double slit experiment, in which he measured the wavelength of visible light. That is why the experiment, Young's double slit experiment, is considered as first conclusive proof for the wave nature of light. If you measure the wavelength of something, that is sufficient to establish it is a wave. So Davison-Germer experiment, on one side, on one hand, that establishes the wave nature of matter. And one more thing, then it compares the wavelength of the electron beam, measured value of the wavelength of the electron beam, with the value predicted by de Broglie's equation, and it is established that they match. Therefore, it confirms the de Broglie's equation. So we will discuss that. So first we will discuss some ideas related with wave nature of matter. Now we know in 1924 de Broglie suggested matter should have wave character under certain circumstances, and its wave character should be given by the equation lambda is equal to h by p. Now question was to test experimentally. Therefore experiments were set up. One experiment was set up, double slit experiment with electrons. You know double slit experiment with light. What we do, we take two slits, then beam of electrons was made incident on this double slit, then the pattern was observed on the screen. It was experimentally observed, double slit experiment of electron beams, that is the pattern formed on the screen, intensity pattern, interference fringes, they match that of light. That means in Young's double slit experiment, we know when double slit experiment is performed on the screen, a pattern is formed of dark and bright bands, which we call maxima and minima of intensity. And we know if something shows interference, it is experimentally sufficient to conclude from that this particular thing is behaving like a wave. And when we compare the interference pattern of this double slit experiment with electrons with that of light, it 100% matches. Then diffraction experiments were observed with electron. We know diffraction pattern of light at circular aperture. What is the pattern? There is the central maximum disk is formed, then there are secondary maxima in the form of rings like this. It is what? It is diffraction pattern at circular aperture with light. When diffraction pattern at circular electrons is conducted, same pattern is formed, which establishes diffraction is also proof for wave nature, which establishes electrons are really behaving like a wave. Then question was to generalize this wave nature to all matter, because it is not necessary. What is the behavior of electrons will be behavior of all matter. Therefore, the particle was changed. Neutrons were taken. Neutrons are different from electrons in many ways. One, it is neutral, electron is negatively charged. One more thing, electron is fundamental, neutrons are composite particles, they are comprised of quarks. Mass of neutron is very large compared to electron. Approximately 1836 times more massive is neutron than electron. So it is different particle. Double slit experiment was conducted with neutrons, and it was seen, it also shows the pattern same as that of light. Then helium atoms were taken. They also show interference pattern. Now problem is one thing, as our particle becomes more massive, diffraction and interference pattern becomes less convincing. That means the interference pattern and diffraction pattern of electron beam will be more pronounced than that of neutrons and helium atoms. Why so? We know de Broglie says lambda is equal to h by p, and we know double slit interference or diffraction pattern, to make it pronounced there is a condition that wavelength of the wave should be comparable to the dimensions of the slit. Only then diffraction will be substantial, it will be pronounced. Therefore, if you want interference pattern or diffraction pattern with helium atoms, you should have slit of that size as that of the de Broglie wavelength of these particles. But we see one thing from this: h is very small, 6.6 into 10 raised to power minus 34 joule second. It is very small value. So when we talk of macroscopic particles like some stone, its momentum will be large. H is very small, therefore lambda will be very small. We don't have slits that small which can exhibit the interference pattern of some stone, interference pattern of something which is of macroscopic size. But for subatomic particles, their mass is small, their momentum is small, therefore their wavelength becomes comparatively larger, therefore for them we have slits available. That's why we say at in macroscopic world, this wave nature has no significance, because the wavelength, de Broglie wavelength, will be very small for macroscopic particles. So it has no significance there. Now it is established, then it was generalized that this property, that matter in certain circumstances behaves like a wave, it is true for all matter. Now what is the experiment? Davison-Germer experiment, which experimentally confirms de Broglie equation and experimentally measures the wavelength of electrons. We will discuss that. Davison-Germer experiment. What is being done in this experiment? Davison-Germer experiment took nickel crystal. It was nickel crystal. Then a beam of electrons, electron beam, was made incident on the nickel crystal. Then it got diffracted from the nickel atoms. We call this diffracted beam. Then this diffracted beam was observed by the detector. This was a detector here, at different angles phi. The idea was this: electron beam was generated from the filament by means of applying voltage across it. Now electron beam was generated, then in its path it was accelerated. We know if electron which has charge E is accelerated through potential difference V, if it starts from rest, then the kinetic energy attained by the electron is eV. If electron starts from rest, if it is accelerated through voltage, potential difference V, then the kinetic energy attained by the electron will be eV. The electron beam was created by Davison and Germer. Then the beam was accelerated through different voltages. When it was accelerated through different voltages, that means the kinetic energy of this beam was different, it was varied. And because of that, we know when we write lambda is equal to h by p, if we write in terms of kinetic energy, it will be under root 2m k. K is kinetic energy. Because we know there is a relationship between kinetic energy and momentum. So P can be written as under root 2mk. So that means if you adjust the kinetic energy of the incident electron beam, you are adjusting its de Broglie wavelength. So electrons were taken, they were accelerated through different values of voltages, and they were detected by means of detector at different angles phi. For example, 30-degree electron beam was observed, 40-degree electron beam was observed, 60-degree electron beam was observed, and in the detector these diffracted electrons produced current. That means they were noticed in terms of the current which flowed in the detector because of the electrons received by it, diffracted electrons. It was observed by Davison and Germer that when V is 54 volt and phi is 50 degree, when V is 54 volt and phi is 50 degree, the diffracted beam is most intense, or I can say current in the detector is most intense, maximum. If you change the accelerating voltage V of the electrons, your value is different from this, and you change the value of phi, it is different from this, then the current in the detector, intensity of the diffracted beam will be less than maximum. For this pair of values, intensity of the diffracted beam, current in the detector was maximum. Now question was to explain it. The idea of Davison-Germer was like this. They said inside nickel there are atoms. There are different layers of atoms. Now the spacing between two nickel atoms inside the nickel crystal was known. It was 215 picometer. The idea was when the electron beam, this is electron beam, strikes the nickel atom, it is diffracted. When it is diffracted through angle phi, this is diffracted beam, and it is detected by the detector. Diffraction pattern is formed. Actually, there will be diffraction pattern, and it can be shown that the maxima of that diffraction pattern which is formed by the diffracted beam, equation for locating them can be written as m lambda is equal d sine phi. M is 1, 2, 3 and so on. If m is 1, it is first diffraction maxima, m is 2, second diffraction maxima, m is 3, third diffraction maxima, and so on. Davison and Germer recognized this situation when V was 54 volt and phi was 50 degree. They said it is actually first diffraction pattern of the diffracted beam of electrons. Therefore, the wavelength of this diffracted beam when this situation arises must be d sine phi. M is to be taken as 1. It is d sine phi, and calculated the wavelength. D was 215 picometer, sine of 50 degree, because phi at that situation was 50 degree. When it is calculated, it turns out to be 165 picometer. So they said experimentally the wavelength of the electron beam which we are using in this situation is 165 picometer. It was experimental value using the idea of diffraction. Then they said, what is the predicted value of de Broglie? They said it is h by under root 2m k. K is eV. So they substituted the values, Planck's constant, mass of electron, charge of electron, and instead of this V, accelerating voltage 54 volt was taken. When we calculate this value, it turns out to be 167 picometer. So their idea was, it is experimentally measured value and it is predicted by de Broglie. So this 2 picometer in 165 picometer is very small. So they attributed it to experimental error. they said it is now established, since using the diffraction idea we can interpret this experiment, that electron beam shows diffraction, we measured its wavelength, therefore it is a wave, we compared it with de Broglie wavelength, it matched, therefore this de Broglie wave equation correctly connects the wave nature and particle nature of matter as well as wave. Now it is established thing that matter as well as radiation has dual nature. Matter under most circumstances behaves like particle, but under certain circumstances behaves like a wave. Likewise, radiation under most circumstances behaves like a wave, but under certain circumstances behaves like a particle. Now we have last idea to discuss in this chapter, dual nature of matter and radiation, that is Heisenberg's uncertainty principle. Heisenberg's now it is established kind of thing that matter is wave-like as well as particle-like, radiation is wave-like as well as particle-like. We cannot deny this dual character because it is experimentally confirmed. Now question is to reconcile these. First, why we feel uncomfortable when we say something is wave as well as particle? There is reason for this. When we say something is wave, wave by definition is delocalized in space as well as delocalized in time. What is meaning of that? Meaning of that is, if some wave is going along some string, for example, there is some string, some wave is going through the string, you photograph it. At some particular time, you want to locate it, where it is. When you photograph it at a particular time, in order to locate the wave, it will be present everywhere. You cannot pinpoint that this wave is present at t is equal to 0 or t is equal to 1 second, at x is equal to 1 centimeter, x is equal to 2 centimeter, you cannot pinpoint it. That means it is spread over space. That means it is delocalized in space. Likewise, it is delocalized in time. What does that mean? If some wave is coming from this side and you station yourself at this point P in order to receive the wave, wave is coming. Now, when wave passes through your point P at which you are going to receive the wave, wave will not transport through your point of observation in a flash, in no time interval. That means there will be arrival time of the wave at point P, and accordingly there will be departure time for the wave. That means when wave arrives at P and when wave leaves from the P, between those moments there will be an interval. That means wave will be delocalized in time. But when we say particle, particle is localized in position, space as well as localized in time. That means if some particle is moving along this x-axis, I photograph it at particular time, I can pinpoint it. It is at this point, time. I can pinpoint its position coordinate. That means it is localized in space. Likewise, it is localized in time. If particle is moving along some x-axis, you are at some particular point to receive it, it will be a flash over which it will pass through that point. That means when it passes through the point, there will be no arrival time and departure time for the particle. Particle arrives and particle leaves. The moments will be same. There will be no interval between the time it arrives at point P and it leaves from point P. It departs from point P. That means particle is localized in space as well as localized in time. Since wave characteristics and particle characteristics are 100% contradictory to each other, wave is delocalized in space as well as delocalized in time, particle is localized in space as well as localized in time. That is why whenever we talk of this dual nature, we become uncomfortable to reconcile this. But since it is experimentally established, our being uncomfortable will not nullify this idea. This is a fact, experimental fact. Now we have to discuss uncertainty principle. Now it is experimental fact now that matter has dual character, wave has dual character. The question is to reconcile these ideas. How can we localize? Can we first represent particle in quantum mechanics, wave mechanics, by its normal sinusoidal wave? Particle on one side is localized in both the dimensions, time and space. If we represent it by some wave, it is delocalized in both. Now, how can we represent by a normal wave? We don't do this. What we do, we represent in quantum mechanics or wave mechanics a particle by a wave packet. We construct a wave packet because wave packet is particle-like. It can be in certain zone. We will understand that. Now when we localize wave in space, from that we obtain a relation, and the Heisenberg's uncertainty principle is derived from that particular relation. Now localizing a wave in space, you will understand it. Listen carefully. If we have some wave, there is some sinusoidal wave, pure sinusoidal wave, it is going along x direction, we at some particular time t is equal to 0 photograph it in order to locate it. When we photograph it, its delta x will be infinity. What does that mean? It will be spread over whole x-axis. This will be its wavelength, and accordingly it will have a wave number. Wave number by definition is 2 pi by lambda. If lambda naught is the wavelength of the wave, then the wave number is 2 pi by lambda naught. Now if we photograph this wave at some particular time, this wave will be spread from minus infinity to plus infinity. That in other words means if we represent particle by this wave in wave mechanics or quantum mechanics, that will mean that particle can be anywhere from x is equal to minus infinity to x is equal to plus infinity. If I say particle is anywhere along the x-axis, that means I don't know its address. Anywhere means nowhere. We have to give the precise address. Therefore, we say we cannot represent the particle by this pure sine wave because it is delocalized in space. It cannot represent particle. It is not particle-like. But there is one good thing about this wave. This wave is pure. Pure means its wavelength has single value. It is not mixture of many waves. It has single precise value of wavelength. Accordingly, its wave number is pure, single value. That means if you show the spectrum of this wave, if it is amplitude, on this side we are representing wave number. It is here 0.5 k naught. It's k naught. It's 1.5 k naught. K naught is the wave number corresponding to lambda naught. It is spectrum. Contains single wavelength. Therefore, the spread of wave numbers making up this wave is 0. It is not mixture of waves. But this wave cannot represent particle, as we have justified. what to do, how to make this wave localized. We have an idea in wave motion that we can construct some waveform by mixing many sine waves. And if we make adjustment in the amplitudes of the mixing waves, frequencies of the mixing waves, phase of the mixing waves, we can make adjustment in the resulting waveform which we get. So it is possible to construct a desired waveform by mixing many sine waves. Therefore, we do the same. We construct a wave packet by mixing many sine waves. This is a wave packet. What will be good about it? When you photograph this wave packet, it will be available in certain zone. It will not be available throughout x-axis from -infinity to +infinity. Because what we do at certain time t is equal to 0, because what we do, we mix wave in such a fashion so that on this side, from this point to -infinity, from this point to +infinity, interference between the mixing waves is such that they completely destroy each other. There is 100% destructive interference of the mixing waves on this side, 100% destructive interference on this side. The resultant wave packet which we get is only spread over certain length, delta x. That means if we represent wave, if we represent particle in wave mechanics or quantum mechanics by this wave packet, it is good. Why? Because this wave packet is available in only certain zone. So if I say particle is represented by this wave packet, that means this particle will be available from this coordinate to this coordinate. So this wave packet is particle-like. It can represent a particle. But what is bad about this? It is not pure wave. That means if we show it a spectrum of this wave packet, amplitude versus wave number, this is wave number, we plot, it is 0.5 k naught, it is k naught, it is 1.5 k naught, it is 2 k naught, it is like this. This means to obtain this wave packet, we have mixed many waves having different amplitude, many waves having different wavelengths, hence different wave numbers having different amplitudes in order to obtain this. That means purity of the wave is sacrificed in localizing the wave. Here wave was pure, it was containing single wavelength, single wave number, but it was delocalized in space. Now what we do, we mix many waves in order to make wave localized in space in order for this wave to represent the particle, in order to behave this wave particle-like, but in order to construct this wave packet, we have to mix many waves having different amplitudes, different wave numbers. Now the waves contained in it, hence the wave numbers contained in this wave packet have a spread of values, delta k. Now what is the best possible situation in constructing this wave packet? Best possible situation is to make it 100% particle-like. That means to make delta x 0, because for particle delta x is 0, because we can pinpoint the particle. That means best possible situation can be mathematically written as delta x delta k is approximately 1. Why? Because more you make this particle like, more number of waves you need to mix. That means if you have to make delta x approaching to 0, delta k has to approach to infinity. That means delta x is equal to 1 by delta k. If delta k approaches infinity, if infinite number of waves you are mixing, it is possible to make the wave 100% localized, 100% like particle, make delta x 0. But it is the best possible situation. More appropriately, to include the situations which are worse than this. Worse than this means your particle, your wave packet has some extension in space. It is not 100%, you cannot pinpoint it. Delta x is not perfect 0. Then delta k will not be perfect infinity. So therefore, in order to incorporate those situations also, we write greater than or equal to 1. Because if delta k will be less than infinity, delta x will be greater than 0. The best possible situation is equality, and worst situations are included in this greater than. This is how we localize wave in space. By mixing many waves, we construct wave packet. Now, but advantages, we are localizing the wave. Disadvantages, wave is becoming impure. Its wave number is becoming less precise. And when we talk of this wave number precise, it is connected to wavelength. Wavelength in turn is connected to momentum. We know lambda is equal to h by p. That means if I represent some particle by this wave, disadvantages, it is 100% delocalized in space. Delta x is infinity. We cannot represent particle by this wave, but it is pure. Since it is pure, its wavelength is pure, its momentum of that particle will be pure. So in order to make position precise, k will become imprecise. Hence, momentum of the particle will become imprecise. So there is trade-off between the purity of the position and momentum. If you want to make position more precise, momentum becomes imprecise. Momentum you make precise, position becomes imprecise. And the condition connecting these things is this relation. When we write this equation, delta x, delta k is greater than or equal to 1, we are not writing it 100% exact. We are missing certain waves. We are taking only middle portion of the waves. When we do it 100% mathematical analysis, calculate it 100%, it is actually half here. But we are writing here 1 because that will not introduce much error. Now when we introduce this equation to de Broglie waves, what we get? Delta k for de Broglie waves is delta 2 pi by lambda, and lambda for de Broglie waves is h by p. So I will write it like this. Therefore, delta x, delta k greater than or equal to 1, I can write delta x, instead of delta k I will write delta 2 pi p by h greater than or equal to 1. It was 2 pi by lambda, instead of lambda h by p upar aayega. So then I write it delta x, delta p is greater than or equal to h by 2 pi. Now since momentum is a vector quantity, when we talk of x position, we talk x component of momentum. That is here px. It is here px. Likewise, we can obtain delta y, if we talk of y position, delta py is greater than or equal to h by 2 pi. Likewise, for z coordinate, delta z, delta pz is greater than or equal to h by 2 pi. Now these three equations, this one, and this one, they are called Heisenberg's uncertainty equations. They are given by Heisenberg in 1927. Now what is the conclusion of these equations? Conclusion is, it is not possible to determine position and momentum of a particle with unlimited precision. There is a limit in the nature. You cannot make momentum and position of a particle precise to any arbitrary level. See, if you are measuring momentum to certain precision, your position precision will be at least h by 2 pi delta p or greater than that. At least is this. That means your delta x cannot be less than h by 2 pi delta px, because it will be greater than or equal to. The best possible situation is your least precise delta x will be h by 2 pi delta px. That means once the precision of momentum is fixed, automatically the precision of position is fixed. It can be equal to this or greater than. It cannot be less than this. That means you cannot localize particle to any extent, knowing its momentum to some extent. Likewise, if you know the position of the particle to some extent, you cannot know its momentum to any extent. In quantum mechanics, we say this statement that nature has restricted us. We cannot know about nature more than it allows us to know. We can know about the nature only to the extent it allows us to know, because this is a restriction. And this restriction is because of dual nature of matter and radiation. Here, matter. And one more thing, if I write exactly here half, then it will turn out to be exact relations are h by 4 pi in all the three equations. And you have to remember why we write it h by 2 pi. We sometimes write just h because h is very small. Its value is 6.6 into 10 raised by minus 34 joules second. So whether you write just h by 2 pi or h by 4 pi, it will introduce a minor error in the equation because h is too small. And one more thing you have to remember about these relations. These relations assume ideal instruments. It is not because our instrument has error and we cannot know to any extent about the position, knowing momentum to some extent, or we cannot know momentum to any extent, knowing position to some extent. It is assuming ideal instruments. This restriction is in the nature itself. It is not because of instruments. Instrumental error will be in addition to this. It is assuming ideal instruments. Now, in macroscopic world, this uncertainty relation has no significance. For example, if you take some stone having certain mass, moving, for example, having size of 10 centimeter across, then calculate its position uncertainty. It may be in, for example, 1 picometer. It is meaningless or absurd to find 10 centimeter across stone in 1 picometer zone. So it is there useless. But in subatomic world, if there is some electron and you find that delta x for electron is 1 picometer is a huge distance for electron. You need to know in 1 picometer zone where it is. But your position there is imprecise. But in macroscopic world, it is useless. It has no significance. So this was about uncertainty principle. Now here, dual nature of matter and radiation chapter is concluded. Now we know matter as well as radiation has dual character. It is established. We know photoelectric effect. What is the effect? What are experimental findings? And we know that wave theory cannot explain it, then photon theory can explain it. We discussed that. Then we said the experiment which establishes the wave nature of matter, Davison-Germer experiment. Then we discussed the uncertainty principle. Okay, God bless you. Thank you.